Okay, so we could make a start. So just want to recap on something in the last lecture where some people pointed out I'd made a typo. Remember, we had this equation here, diffusion equation, initial condition, boundary conditions. So these boundary conditions, it's a Fourier sine series. And then when I wrote out the solution, I forgot to put this one in here. So of course, you know, it's this is the coefficient of the Fourier series. So put that in, and then e to the minus this. And then I forgot to add that, but a number of you spotted that, so thanks for pointing that out. Okay, so remember what we did the last time was we solved the equation, and then we talked about different types of properties of the diffusion equation. So before we go on to prove uniqueness, I want to do one last example in this setup. So again, we've got the heat equation or diffusion equation in general. Again, 0 less than x less than L, t bigger than 0. And we're going to have boundary conditions as before, homogeneous Dirichlet boundary conditions at 0. And now we're going to have our initial condition or initial value, same thing, is going to be f of x equals 0 if 0 is less than x less than or equal to L1, and L2 less than or equal to x less than or equal to L, where L1 is less than L2. And then it's going to be 1 otherwise. So it's going to be 1 if x is less than L2, bigger than L1. Okay? So in other words, if this is 0 and L, then f of x is going to be 0, except if you're in this region. So 0 to there, and then it's 1 here. Okay? So what that means is that you start off, if you think of it as a heat equation, you start off by heating this amount of the this part of the rod. If you think of this as being a diffusion of a chemical, then you can think that you start off and you put some chemical here. Okay? So now to solve this, you do the usual thing. You do separation of variables. So again, I'm not going to write out all the details, leave you to do that. And then you do the usual thing. You find out that f double dashed over f must be a constant. And then you can say if that constant is 0, then with these boundary conditions, the only solution is 0. If that constant is positive, you get hyperbolic cosines and sines. Boundary condition means they're 0. So if the constant is negative, you get sines and cosines. Boundary conditions mean that the only non-negative solution or non-zero solution you can get is sines. Okay, so it's the usual thing. And then you end up getting that t of xt must be the sum, n goes from 1 to infinity, an sine n pi x over L times e to the minus n squared pi squared kappa t over L squared. And then as usual, or well, bn, we've been calling these b's, I guess. Then as usual, in order to now satisfy the initial condition, we need to be able to write this function as its Fourier series. So we do the usual thing. We do the periodic extension of that to get the Fourier sine series. And then we find out that the bn's turn out to be 1 over L integral from minus L to L. And this is the odd extension of f, odd periodic extension of f, sine n pi x over L dx. And that just comes down to be 2 times from 0 to L, f of x sine n pi x over L dx, okay? The usual thing. And then that's just going to be integral from L1 to L2 sine n pi x over L dx. Okay, because f is 0 except if you're between L1 and L2 when it's 1. And so you can work that out. That's just going to be cosines. Okay? So then we've got, if I've got the signs of these correct, finally we get t of xt equals 2 over L pi, if I've got this right. Sum n goes from 1 to infinity, 1 over n cos n pi L1 over L minus cos n pi L2 over L times sine n pi x over L times e to the minus n squared pi squared kappa t over L squared. Okay, so again it's just exactly the same as we've done before. You see that the only difference in all these calculations, the only calculation you really have to do is work out the coefficient, the Fourier coefficient. Okay, so now if we look at that equation there, what we can see is as soon as, so for t equal to 0, then this is the Fourier series of the f, which is that thing there. Now if we were to plot this for t just slightly bigger than 0, and this is done in the notes, and this is something you might want to do yourself, what you will see is that t of x of t is immediately bigger than 0 for all x that lie in 0L. Okay? So in other words, if you think of this function, if you think of t of xt, and t of xt started like this, then was 1 here, that's supposed to be 1. Okay, so it was a discontinuous function to begin with, went to here, jumped up to here, jumped down to here. As soon as t becomes bigger than 0, 2 things happen. Firstly, this smoothens out. It becomes a smooth function. And the second thing that happens, so 1, it smooths out. And the way you can get that would be if you just plotted these solutions. And the second thing, if you plotted the series, should say, is that it's got infinite speed. In the sense that you started off, it was 0 here to this point here. As soon as t becomes non-zero, this becomes non-zero everywhere. So even though I've drawn this coming very close, you know, it doesn't really get, it's slightly above 0. Okay? So from a mathematical point of view, there's nothing wrong with that. But from a physical point of view, you see this is one of the limitations of this model. Because physically, things don't travel at the speed of light, or at an infinite speed, okay? Unless you're talking about energy costs. Things do not travel at infinite speed, okay? But the fact is, these values here are so incredibly small, it doesn't really make any difference. So this doesn't mean that this model is useless because it makes an unphysical prediction. These values are so incredibly small that essentially it's not going to affect the use of the model. Okay? So that's just one thing to keep in mind. Right? So now we get to the thing where all along we've been making all these assumptions that we've got the solution. But what happens, we looked for a very special type of solution, a separable solution. Maybe there might be other solutions that you can't write as separable solutions. So now what we're going to show is that the solution to this problem is unique. So if we can find a solution, whichever way we do it, it's the solution, okay? So this is uniqueness. And so the theorem is that the initial boundary value problem has only one solution. So the way we do that, typically the way you show uniqueness, is you prove by contradiction. You assume that there are two solutions, and you show that those two solutions must be identically equal to each other. So assume, so we'll start off with the problem dt by dt equals kappa d2t by dx squared, 0 less than x less than L. So it's the problem now, this is the third time we'll have written down this problem, and assume that t of 0 t is t of L t is 0 for all t bigger than 0, and initial conditions t of x0 is f of x for 0 less than x less than L. Okay? And now assume there exist two solutions given by t1 of xt and t2 of xt. Okay, then w of xt, which is t1 of xt minus t2 of xt, that satisfies the heat equation. Okay, so the way you can prove that is you can just say this is a linear equation, and so if we have two solutions to the linear equation by the principle of linear superposition, any linear combination is a solution. and t1 minus t2 is a linear combination. Or you can just say, what is, this satisfies dt1 by dt equals kappa d2t1 by dx squared. Do the same thing for dt2, and then just subtract them. And you'll get the d by dt of t1 minus t2 equals kappa second derivative of dt1 minus t2. So either way, you've got that. But now you've got that w of 0t equals, in fact, we could go even further than this. We could have this not 0, but or a constant, or non-zero constant. In fact, not equal to 0. It could be negative, not equal to 0. Okay? Well, it wouldn't be negative if you were talking about a density or something like that. Okay? So w of naught t equals w of lt equals 0 for all t bigger than 0. Okay? So if t is fixed on the boundary, whether it's fixed at 0 or at some positive value, then w will be 0 on the boundary, because t1 and t2 will have to be the same value at the boundary, so t1 minus t2 will be 0 at the boundary. And what about initial condition? W of x 0 will be 0 for x naught than L, x bigger than naught less than L, simply because t1 will be f, t2 will be f, so t1 minus t2 will be 0. Okay? So what we have is, we have the diffusion equation, and we start off with no w on the boundary. So if you think about this in a physical sense, we start off with, say, this is the diffusion equation. Think about, you start off with a box, and there's no chemical in there, and you don't put any more chemical in. What you would hope is that your equation would tell you that there's no chemical in the system. Okay? So what we want to show is that w is equivalent to 0 for all time and all space. And then if w is equivalent to 0, then that means t1 is equal to t2. Okay? So how do we do that? We start off with I of t equals the integral from 0 to L x of t dx. And I think in the notes, put a half in there if you want. Okay, so basically what we want to do is we want to show, if we could show that this is 0 for all time, then it follows that w is 0, equivalent to 0. Okay, that's w squared, so it should be like that. All right? So one thing we know is that I starts off at 0. This tells us I is bigger than or equal to 0. So if we could show that di by dt was equal to 0, then it would follow that I is equal to 0. Okay? So that's what we do. Di by dt. Now we use Leibniz rule. Since these don't depend on t, we can take the d by dt, we can swap that with the integral, and we get integral from 0 to L. Differentiate this by the chain rule, we get this. And then you can see why the half is put in there just for convenience. You get the 2, and then you get 1 there. Okay? And then the usual thing you do here, this is very common. dw by dt is kappa d2w by dt squared. Kappa is a constant, take it outside. Equals kappa, and now we do chain integration by parts. So that's u by dx, evaluated at 0L, minus kappa integral from 0 to L, v du, d2, or dw by dx squared, dx. Okay? Therefore, di by dt is, well, this is 0, because w is 0 on the boundary. Okay? So that's 0 minus kappa integral from 0 to L dx. And so that tells us that di by dt is less than or equal to 0. Okay? Because this here is greater than or equal to 0, multiplied by minus, less than or equal to 0. So I started off at 0. di by dt for all t is less than or equal to 0. So that implies that I of t is less than or equal to 0 for all t bigger than 0, given I of 0 equals 0. So what we've shown is I of t must be less than or equal to 0 for all t. What we know from up here is that I of t must be greater than or equal to 0 for all t. So the only way those two conditions can hold together is if I of t is equal to 0. So that implies I of t is equivalent to 0. And that implies that t1 is equivalent to t2 for all, I should put in x of t here, x and t in the domain, okay? X element of 0L, t greater than or equal to 0. So we've got uniqueness. Uniqueness. Okay? So this is quite a common occurrence. This is quite a common thing when you're proving a result like this. You start off with the square, you then differentiate with respect to t, you then go back to your equation and substitute what that is in here, and then you integrate and you get through. So one thing to note is this also works for Neumann conditions. Neumann boundary conditions. Remember what Neumann boundary conditions would be a condition on the flux. So if we had conditions that dt by dx at 0 t was equal to t1 and dt by dx at lt was equal to t2, then w would satisfy dw by dt is equal to 0. dw by dx is equal to 0 at 0 and L. And so this would be 0. Okay? Likewise, just to be clear, if we had up here t of 0, t was equal to t1, t of lt was equal to t2, then once again, w would be 0 on the boundaries. So it doesn't matter what type of Dirichlet boundary condition you have, what the constant is equal to, and there can be two different constants. Likewise with the flux, as long as when you take, sorry, I shouldn't call that T1 and T2 because that's what we've call that T star as constants. You can see that as long as W or dW by dx are 0 on the boundary, that will be 0, and then we've got di by dt is less than or equal to 0. In fact, this would also work if this was negative on the boundary. So it doesn't have to be 0 on the boundary. It could be negative, and then it would still work. So NB works for any boundary conditions such that W dW by dx evaluated at 0 and L less than or equal to 0. Okay. So that's our uniqueness solution. So now we can say that because our solution is unique and we found a solution, that is the solution. Okay, so now we'll move on to what would happen in the system we call, I'll explain what these things mean, non-zero steady states. I'll explain what that means in a few minutes. So suppose we have the following initial boundary value problem. dt by dt equals kappa d2t by dx squared and initial condition or initial value okay, so that's identical to what we've had before, and then we've had boundary condition t of 0t equals t of LT equals for t bigger than 0, and normally we've put 0 in here. So suppose instead of that we had some t star, where t star is some constant. Okay, and if we were dealing with, if this was a chemical, then that constant would have to be bigger than 0. So now suppose we try to do separation of variables. Separation of variables. Right, because it's worked very well for us over the last 3 weeks, so let's continue using separation of variables. T of xt equals f of x g of t. And now we need to find what are the boundary conditions. So boundary conditions, f of 0 g of t equals t star, f of L g of t equals t star. Now beforehand this was 0, so then we said f of 0 is 0. This was 0, f of L is 0. Now if this is not 0, see f of 0 is a value, it's a constant. This would mean g of t is a constant. It's true for all t. So t star not equal to 0 will imply g of t equals a constant for all t bigger than 0. And that would imply t of xt is a constant in time. But that's wrong. It's not a constant in time. Because if you start off with a distribution of t, it's going to diffuse and it's going to change over time. So this is wrong. It's a contradiction. T changes, big T changes in time. It depends on time. So the separation of variables doesn't work. And it doesn't work because this is not 0. Okay. So it would be, if only that was 0, then it would work. So if only we could take this away, then there would be 0, and everything would work. Okay, so let's do that. Let's just look, instead of looking at t, let's look at t of xt minus t star. Let's call that s of xt. Or no, call that w of xt. Now look at that w. W of 0t is equal to 0. And that's also w of lt for all little t bigger than naught. And so now we've got rid of our problem. Right? Now we've got that this is 0, this is 0, so we're back to where we were beforehand, that we spent the last 6 lectures doing. Okay? So that's good. But now the problem is, what equation does w satisfy? dw by dt equals dt by dt minus 0. Because differentiate a constant with respect to little t, you get 0. And what about d2w by dx squared? That equals d2t by dx squared minus 0. Because you differentiate a constant twice, you get 0. So w satisfies the same equation as t. So now we're back to the problem that we've just been solving. And the initial condition for w of x0 is equal to f of x minus t star for x. So now, if we look at this problem, everything works. So now look for solution of the form f of x times g of t. Usual argument, f double dashed over f must be a constant. If that constant is 0, then by these boundary conditions, f has to be 0, so you get 0 solution. If that constant is positive, then we get hyperbolic sines and cosines. This boundary condition means those must be 0. And then we have, if the constant is negative, we get sines and cosines. This boundary condition, say, must be sine, and the constant must be n pi over L. So we've got a Fourier sine series. And now what about the, how do we find the Bn? The Bn is the Fourier sine series of this term here. And that's it. We're done. Okay? So funny thing is, we've taken the T star out of the boundary condition, and we've sort of put it in to the initial condition, where it doesn't do any harm. And so it works. So that's the trick. Okay? Now, this trick, it was very lucky that this worked. It was very lucky that the T at 0 and T at L were the same. What would happen if they weren't the same? Suppose instead T of T of 0, T was T naught, T of L, T was T1 for all T bigger than 0, and T naught not equal to T1. So now we can't do that same trick, right? Because if we tried W equals big T minus T naught, then the boundary condition at x equals naught would be naught, so that's fine. But the boundary condition at x equals L would not be naught. And then that's a problem we have again. Okay. So now we do a trick. We look for steady states. Now, a steady state, what does that mean? Steady means it doesn't change in time. So it means that, look for steady states, call them S. S just depends on x. Okay? So then we have, well, we have ds by dt equals kappa d2s by dx squared. And this is 0 because it's a steady state. It doesn't depend on s. It doesn't depend on t, I mean. So that must be, so this becomes an ordinary derivative. Okay? If d2s by dx squared is equal to 0, then we integrate up, we get s equals ax plus b, where these are constants. And now suppose s at x equals 0 is t naught, s at x equals L is T1, then if you do a bit of algebra, you get S must be T naught plus T1 minus T naught over L times X. So leave you to do that. Let's just check. S of naught is T naught. S of L is T naught plus T1 minus T naught. So that works out. Okay, good. Right, so what's the point of doing this? Now let's put and now I'll use the notation that's used in the notes. Sorry, he used U in the notes, not W, so sorry about that. Let's now put U equal to T minus S. Now if we look at that, U of 0t is equal to, well, T at x equals 0 is T naught. S at x equals 0 is t naught, so that's 0. What about u at L t? It's t at L, which is t1, minus s at L, which is t1, so that's 0. So we've got, once again, we've managed to get zeros on for the boundary condition. We've managed to reduce the problem to a homogeneous Dirichlet problem. And now the problem is, but what equation, differential equation, does u satisfy? Well, let's look at du by dt. Du by dt is d by dt. And what's s, differential with respect to little t? Well, s is a function of x. Differential with respect to t is 0. Minus 0. What's the second derivative with respect to x? Now it's, oops, well that's certainly true. Doesn't get us anywhere. That's bad. Okay, so d2u by dx squared is d2t by dx squared minus d2s by dx squared. So what's d2s by dx squared? Well, by construction, d2s by dx squared is 0. So this implies that u satisfies our diffusion equation, or heat equation. Right, so now we've got the heat equation, we've got these as our boundary conditions, and what are our initial conditions? U of x naught is equal to t of x naught, and t of x naught was fx, minus s at t equals naught. Well, s is t naught plus t1 minus t naught over L times x for 0 less than x less than L. And so now we've got our setup. So now we look for separable solutions. We get f dashed over f must be a constant. If that constant is 0, then these boundary conditions mean you've got 0 solution. If that constant is positive, it means we get hyperbolic sines and cosines. The boundary conditions mean must be 0. So then we've got constant is negative, sines and cosines. Only non-zero solution is sines, and the constant is n pi over L. And so now we've got a Fourier sine series. How do we find the coefficient of the Fourier sine series? We have to take the, sorry, that was a bit, that should be like that. We now have to take the Fourier sine series of this. So we've just changed the initial condition. Okay. And so in fact, if you go back and look at this problem here, what we did here was exactly the same as what we've done here, because in that problem t1 was equal to t naught. So in that problem our steady state was t0. So in fact what we had done here was we had used the fact that t0 is a steady state. Because in this problem, d2s by dx squared equals 0 means s equals ax plus b, but s was equal to, t star. S was equal to t star on both boundaries. which means S means that the A that multiplies the X must be 0, and the constant B must be T star. So you see, finding the steady state of the system and then taking that away means that the problem of the boundary disappears and is replaced. These come in here. Okay. So that's the trick you use when you have these setups. So when we solve this now, so what we will then get is t of xt equals s, which is s of x, plus u, which would be the sum, n goes from 1 to infinity, bn sine n pi x over L times e to the minus n squared pi squared kappa t over L. Yeah, that's it, where bn is 2 over L, integral from 0 to L, f of x minus t naught plus t1 minus t naught over L times x times sine n pi x over L dx. It's over L squared, yep, thank you. That's absolutely right. Okay, and so whatever the f is, we would put that in here, and then we'd integrate that up. Okay? So now a question we might ask is, how does this behave as t increases, little t increases? As little t increases, this term here will go to 0. So in fact, t of xt will tend to s of x. It will tend to the steady state. Okay. So if we wait long enough, so if we start off, so what this is telling us is that if we start off with this rod and we fix one end to be t naught and we fix the other end to be at t1, then it doesn't matter what the initial conditions are, whether we start off and we put a lot of heat at the beginning or we put no heat at the beginning. In the end, the system will behave as if it was just t naught at one end, t1 at the other end. Okay? So what this means is, if we were to start off, suppose we were to start off with initial condition f of x equals 0, for 0 less than x less than L, f of x equals 0, okay? So in other words, we start off where we have t is t naught there, and it's t1 there, and here's a steady state, s. And our initial condition are that it's 0 everywhere. So I'm drawing it's 0 everywhere. In fact, it's better if you look in the notes, because you'll see this in the notes. And then, of course, it's 1 here, or it's t naught here, I should say, and t1 here. And now, once again, as soon as you start, the little t becomes bigger than 0. This will go down like this, and it'll be slightly bigger than 0 all the way along here, slightly bigger than 0. This will come down here and be slightly bigger than 0, slightly bigger than 0. So once again, we've smoothened out the discontinuous temperature into a continuous thing, which is what diffusion does. It makes things smooth. And also the heat has propagated from the ends right along all the rest of the rod. Infinite speed of propagation. And then as time increases, this will grow and grow and grow until you get to here. As T increases. And then you'll reach the steady state. Okay? And again, as we know from what we've just proved, the solution to these problems are unique. Because if you've got fixed at either end, then if you look for T1 minus T2, difference between two solutions, they'll have 0 at either end. And then we can go through, do our usual analysis, and the solution is unique. So this is the solution that we've got. Okay? So what that tells you here is that you've got a steady state solution and the system evolves to that steady state. So what we will do the next time is we will talk about some other mixed boundary conditions. What happens if you've got Neumann at one end and Dirichlet at the other end? How do you solve that? And then we will also talk about what happens if you've got a source of heat. So that you've actually got, the heat is not only diffusing, it's also being produced. Maybe you're heating the thing up. Okay? And then we will see how you solve those. And then once we've done that, we will then move on to the next chapter, which will be solving the wave equation. So that's the equation d2y by dt squared equals d2y by dx squared. Okay, so it's basically putting a 2 in here. We'll do that one. So we'll do that next time.